So, one of the other things with symmetric keys is that you and your party have to establish ahead of time what key you're going to use, because you're trying to talk to someone on the other side of the internet, or the other side of the globe through the internet, and you can't just tell them, I'm going to use this key, because you haven't set up a secure medium between them. So there's an algorithm actually to exchange keys, and I guess we'll do a live demo of this. Does anybody want to be a volunteer? Sure. And we'll demonstrate this with food coloring, and then I'll show you the math behind it. So here I have 2 glasses of water, and the idea is we want to, in the end, come to have the same color in our glass without telling each other exactly what the color is.
I'm drawing the dot.
Oh, yeah. I think it's on. Okay. So, this is the way it works. We're each going to negotiate a color publicly. It's fine if anyone hears, because you'll see what it'll be used for. So, what do you want to do? You want to pick what color?
Let's pick yellow.
Yellow. Okay, so I'm going to take a drop of yellow and put it in mine. And Richard is going to do the same. Slow tap. Okay, so we both have yellow right now. Now what we're going to do, so this third bottle here, this is our eavesdropper. We call her Eve. And she's going to try to find out what color we're going to get to in the end. So she knows right now that we use yellow because we communicated this across the internet. Now what we're going to do, I mean, yeah, you can put yellow. Okay. It's fine. She's going to try to copy us. Now what we're going to do is me and Richard, we're going to independently pick random colors without telling each other what we picked. And we're going to add that to our mixture. And this is not sent across the internet, so Eve doesn't know what just happened.
Would Eve pick a random color herself?
I mean, she can.
Maybe she doesn't think I was
Okay, so now what we'll do is this is the secret. We're going to trade our mixtures across the internet. So I'm going to get his, and he will get mine. And Eve, you have to assume that the mixture of colors is kind of hard to reverse. You can't take one color and subtract something else. So Eve sees 2 mixtures of colors, and she doesn't know, she knows yellow was one of them, but she can't subtract it to get what the other one were. What I'm going to do now is add the same color, so I added green to mine, and I'm going to add the same color now that this is Richard's glass. And Richard is going to do the same, the color that he used in mine.
I used red, right?
Yes. And now we've come to
Deep dark
Black.
yes, we've come to the same color, all without telling each other what we've decided. And 5 minutes. Whoa.
Whoa.
That's a bug.
Okay. Oh, you're the...
Oh, okay. All logging in. Okay, so the reason this worked .
You want me to blank the display?
Sure.
That's Zoom.
That's not.
Okay. So we both added yellow. Then I added green, and he added red. Then what we did was we took this and traded. So I have yellow-red, and he has yellow-green. Then we added the same secret color again. And the addition of colors doesn't matter. You can add the colors any way you want, and you'll get to the same result. And Eve, who was listening, can't figure out what we did. So that's how we saw. This is called the Diffie-Hellman key exchange protocol, and this happens quite a lot, honestly. in many applications where you use symmetric key encryption, you have to negotiate on a key. And this is one of the more popular methods. I'll talk about another one later. Can you log into the
Yeah.
So we also have asymmetric encryption. And the way that works is you have a different key that's used to decrypt compared to the encryption one. So you have to wonder, how does it all work? Well, the two keys are mathematically linked. You can't just pick two random keys and it'll just work. So there's a whole process for generating keys
I don't know the IP address of that machine.
anymore, right?
Yeah.
Can you give it to me?
Yeah, in a sec.
So asymmetric encryption, you can think about it as I don't know how to draw a lock, but that's a lock. And that's a key. So, back to that example again. So say we're Alice and Bob, and then we have Eve here trying to listen to us. Now, suddenly Alice becomes very popular and she needs to talk to many people at once. Alright, there's many people here. So say she's at bank, right? Well, what Alice needs to do is she needs to negotiate on symmetric keys with each person. And not only that, she has to store them so she can use them later to talk to them. And that is kind of a big problem. So what we have now is we have asymmetric encryption, where we can publish what's called a public key, which is our lock. And then what we'll do, essentially, an analogy, is across the internet, send an open lock to the person. The person closes our lock with their message and sends it back to us. And that way, only we will be able to open the lock with the key. So back to the so that key exchange that I was talking about earlier. No, not the dot. All right. So let's see this better. SSH, whenever you connect to a remote machine, it uses, I believe by default, it's Blowfish, and Blowfish is a symmetric algorithm. So what I did here was I told that I want to connect to one of the machines upstairs, and I put verbose mode on, which is this V right here. And what it's going to do is it's actually going to show me right here when it did a Diffie-Hellman key exchange generation request. I don't know how good you can see that, but so this is where it generated. That's where basically it mixed the colors together. So it's expecting the negotiation between the base color. It sent its mixture across, and it's expecting a reply back. And then once that is done, there's a secure connection that's made, and it's asking for my password. So I'm not sending my password across the internet with anyone being able to see it.
That's no fun.
Yeah, I guess that's boring. Live on the edge. Okay, so let me bring up the PowerPoint again. Too fast. Oh, so actually, I'm going to talk about the algorithm behind that with math, with numbers. So, back to that later.
Like,
Yeah, I'll come back to this example later. But so we need a math function which is easy to do in one direction, like mixing paint, but hard in another direction, which is basically subtracting paint. And this brings us to the discrete logarithm problem. And the way it works is as follows. So modular arithmetic. So modular arithmetic basically is, if if you have a number and you're modding it with something, what you're actually doing is you're taking 46, dividing it by 12, and output the remainder. So this goes in 3 times, I get 36 here, so 10. 10 is my remainder. So the result of 46 mod 12 is 10. And basically, this is what the discrete logarithm problem is. If I have a prime modulus, so this number is prime, say 17, and I have what's called a generator, in this case 3, if I raise it to some power, right, so say x is equal to 1, I can find the result very easily. So 3 mod 17, it's just 3. And then if you put x equal to 2, you have 9 mod 17, that's 9. 3 cubed is 27 mod 17, that's 10, and so on.